Hi everyone. So today I'll be discussing the topic of active learning and the concept of why active learning is important for data annotation and getting awesome training data sets. So I'll start by introducing myself really quickly. So as Will said, I'm the VP of machine learning at a company called Figure 8. Figure 8 used to be called Crowdflower. So more people know us by Crowdflower. So we're basically the enterprise version of Amazon Mechanical Turk. So large companies and AI startups would basically come to us to get training data, because usually when you collect data, you don't have labels with them, and so with those data, and so you have to get those labels somewhere. So prior to joining Figure 8, I was actually working for Atlassian as their chief data scientist. Atlassian, if you don't know, is the company that makes Jira, Bitbucket, Confluence, and so forth and so on. And prior to that, I was actually working for Walmart Labs, basically heading their data science research for the search team. And so a lot of the work I've done was related to getting good training data, and I accidentally became in charge of the person in charge of this, and this is how I learned about how important it is to have high quality training data and how difficult it is to get good labels. I'm also a part of the expert network at a company called IIA, the International Institute for Analytics, and so I basically consult with lots of different types of companies about different topics, including data labeling. And so one of the advantages I have is I have seen lots of different types of data, and I know a little bit about all the different use cases that you can see out there. So let's go back to Figure 8 specifically. So our mission is, as I said, provide, help AI companies, AI teams across the world, get high quality training data so that they can train awesome machine learning models. And so I'll show you what is difficult about getting training data today. And so this is our agenda for this talk. So I'll start by talking about the big data and how big data is important for machine learning. And then we'll talk about the challenge of data labeling, and then I will give you an active learning tutorial and some tips about how to get started with active learning. All right, so why? I mean, I think everybody knows that we live in an era of big data, right? I mean, big data is everywhere, and sometimes people may ask this question, how come this is happening right now, right? And so also, why is it that it makes data scientists and machine learning specialists so happy, right? And so this is what we're talking about today. So we all know that the amount of data available worldwide is growing really quickly. One of the metrics I like to state is typically over the course of 18 months to 24 months, we basically double the amount of data we have, or we collect, as you can see here, right? I mean, so it's really growing extremely fast. And so basically, if you think on those terms, it means that every 18 to 24 months, we basically generate as much data as the rest of humankind before us, which is completely crazy. You probably also saw this in what happens in an internet minute, lots of things happening, because now we have social media, we have IoT, and so there's just a lot of data being generated just because we're very active online. So I mean, you can also ask this question, how come this is happening now? And it almost seems like we have suddenly become interesting as a species, but that's just not the case. So why is it we see so much data today? Because number one, there is a surge in new data formats. 10 years ago, most of the data we were collecting was text. Today, you see lots of different types of data, LiDAR data, which is basically the type of data you collect when if you have a self-driving car, video, lots and lots of images, pictures we take, and audio, and so forth and so on. So the landscape of the type of data we're working with today as data scientists has changed. It's also because we have new technologies, right? So when I talk about new technologies, it's for different reasons that this is helping us collect more data. Number one, we have better storage, we have more storage, we have cloud technologies. It's easier and easier to transfer data quickly from point A to point B. Then we also have social media. Social media is empowering us to deliver and generate data, share data with the rest of the world on a day-to-day basis and at every moment of our lives. Similarly, IoT is also helping us like generate data at the personal level. When you think about like your phone is now capable of recording pretty much everything you do, same thing for your Fitbit. It's just an opportunity that's been created to generate data at a person level when a couple of years back was more of an enterprise level. But then there is another reason why data is growing so quickly, and this is because of data duplication. And so this is kind of important for the rest of the talk, so I'm going to spend some time here. When you do a search on Google, you can do searches for like lots of technical topics. You will always get the same type of results. I search for matplotlib installation, and I get all these different results. But if you actually click on each one of them, you're going to get pretty much the same page with like exceptions around versioning or really minor changes. So at the end of the day, all of these pages are the same information. You'll see the same problem when people retweet things, share things over and over again on social media. So more data does not necessarily equate more information, and that's been a problem for data scientists today. Like big data, which was originally an opportunity, is also becoming a liability because you have more data to process. So now that we've talked about big data, I would like to basically share my views on like why I really think that proper labeling is important, right? So computer vision is a really hot topic these days, but it's actually something that's been around for a while now. So and so the theory about that surrounds like computer vision and deep learning has been around for a while. Like deep learning or neural networks, the concept that goes into deep learning has been invented in the 40s, and going to like computer vision, like there were like basically that was a project started in academia in the late 60s to basically like people believed that over the course of one summer, we would be in a position to have computers understand images better than humans. And as we know, like it's been a while that we're trying to solve that problem, and it did not happen in the 60s because it's really a problem that's much bigger than we thought it would be. But as we all know, like there has been recent progress on computer vision very recently, and actually started to see huge progress like ever since the beginning of the 2010s. And so we have this like a challenge, I think everybody knows here, ImageNet, right? I mean, so there is like this data set that people use to basically like try to improve on the previous version. And so as of like 2015, we now have models that understand images better than humans. So we have like surpassed the basically like it's like a superhuman computer capability, computer vision, right? So how come this has happened so recently? And so my guess for this is that this happened ever since there's been the famous label data set called ImageNet. ImageNet is a data set of like 14 million images, all of which are labeled across like 20,000 different categories, right? And so you just publish this data set, and all of a sudden you have like this spur of new ideas and improved models in computer vision. So this basically tells me that if you have high quality training data, you can actually do a lot of things with it. And this is why we could never do anything before, because getting 14 million labeled images is just something you cannot do on your own. All right, so now that I hope everybody's convinced that getting big data and label big data is key to advanced machine learning research, let's talk about like the concept of labeling. What happens when you're labeling? So we were facing a huge problem. I will say that where our problem as data scientists a few years ago was to collect data, now it's shifted to label data, and I call that the big data labeling crisis. Basically, if you think about this huge amount of data, we've just reached the point recently where even if every single human on the planet would just like do nothing else but labeling, we wouldn't have enough manpower to take care of everything. And so it's a problem because you have all of this data available to you, but you cannot do anything with it unless it's labeled properly. So you have two ways to address the problem. Either you label faster using a machine learning algorithm, or you label smarter, and we'll talk about that in a minute. But I'll start by explaining what labeling faster means. So this is an example of a tool that we have developed at Figure 8 recently. So, and it's basically our video annotation tool. Video has been a problem because if you want, like, if I'm a self-driving car company, Tesla, Uber, like Waymo, you need to label or put bounding boxes. So basically put rectangles around the people or different types of ontologies on an image before you can train a model, right? And so this data has to be extremely high quality, because if you miss a pedestrian in your image, you can basically, like, that maybe make the difference between life and death when you actually deploy a self-driving car software in a self-driving car. So basically, the problem we have is, like, typical videos have like 30 frames per second, and so if you have like a suburban scene like this, like you can have like 20, 30 different like cars per image. So for 10 seconds of video, multiplied by 30, multiplied by 20, that would already take like about 1 hour and 40 minutes for a person to label this manually. And that's assuming that it would take 1 second per box, which is like really unrealistic. Like in real life, that would probably take more, around like 3 to 4 hours. So this is just not possible, right? Because this is 10 seconds. And like if I'm Waymo, I don't need 10 seconds. I need like 10,000 hours of videos to be annotated properly with different ontologies, etc., etc. So what we've done is, like, we created a tool where you annotate the first frame, and then the algorithm basically tracks the objects across the different frames, and you just ask humans to validate what they see. And it's much, much faster. It's actually like increasing the speed of annotation by a factor of 100. And so this is one example of the things we do, but we do that for NLP, we do that for images, we put predictive bounding boxes on images, automated segmentation, and so forth and so on. But just shows you that we've reached the point where you need to use machine learning to provide the training data for other people to do machine learning. So it's a pretty cool area to be in. So this is typically you would use like object detectors that exist on the market. So like YOLO, SSD, RCNN, like these are all like open source version of algorithm that help you identify objects on an image. And so basically, you know that the accuracy is never going to be 100%. So when you have a problematic box like this one over there, you would basically have a human fix it and put it in the right place so that you can reach like a really, really high accuracy. So this is how you label faster. Is it good enough? In my opinion, it's not good enough, and there are actually other things that you can do. All right, so there are other problems like related to data labeling that are not just associated with volume, it's also associated with the difficulty to get the right labels, right? I mean, so when we talk about labeling, what I just showed is like putting a box around a car on an image. This is something that anyone can do quickly, right? There are other cases where it's difficult to obtain because the label is something that a doctor needs to do, right? Or someone who's specialized. It's also something that can be really hard to label. In some cases, labeling means that you need to run blood tests on a patient and you're going to have to wait for some time to get results back for that specific person. It can be super expensive. Like if I want to label like a positioning of oil in the ground to basically validate like my prediction for like where I should put my oil wells, then it may be like thousands or like hundreds of thousands of dollars just to identify basically put a label on your data row. It can be extremely time consuming. So even simple things like identifying a topic for a document may require you to read the entire document. And so if it's like a long, like a 10-page document, then even a simple label is something that can take like a couple of hours or like even a couple of minutes. That would be already a lot of time to improve on. It can even be dangerous sometimes, like if you're just like trying to identify if there is a landmine as you predicted in a specific area, like labeling it would basically mean that somebody has to risk their lives. All right, so now I would like to talk about semi-supervised learning. And so this is something that I guess everybody heard of, but doesn't not necessarily think about when they're building models. So we're all using supervised learning. Supervised learning is like 90% of the machine learning world today. most of the deep learning applications we have today are based on a supervised approach. So supervised learning is when you have label data, and so in this case, if I want a binary classifier between trucks and cars, I'm going to have something, someone, or like a person or a machine that you call an oracle, basically provide those labels for you. You can also rely on unsupervised learning. Unsupervised learning is powerful because it doesn't require labels, but you will just be able to cluster or like create different categories for these different objects over there. You see that all the trucks are in the blue circle, so it's identified properly, but you still don't know that this type of object is called a truck, right? And so this is the weakness of unsupervised. There is a sweet spot in the middle that we don't leverage enough, in my opinion. So it's called semi-supervised learning. And so it's basically this approach that consists in taking the labels you have and leverage the unlabeled data that you have at the same time. And try to get the best of both worlds and try to combine both. So basically, the approach we've taken so far is like when we have a training set, we want to label everything, and we use that to train our models. But you can actually like be smart about how much you label and when you label your data. So you can decide to select basically the data that you think is the most valuable for your model prior to building a model. That would be called something called prioritization. You just try to identify which one of your data points are spam, which ones are hurtful for your model, which ones are useless for your model, which ones are duplicates, right? I mean, because like not like saying that you don't want to use a data point in your training set doesn't necessarily mean that this data is bad. It might be some piece of information you already have. You can decide to make that choice of choosing to use or not use a specific data rows and query a label for it while you're training the model. This is what active learning does. And then finally, you can also decide to like build a model using less data and then use a human like a override position basically to do that. So I can build a model that I know is not going to be accurate, but I'm gonna use like a human in the loop approach to basically take care of the cases where my model failed or like validate. So it's pretty much the same option that we talked about before, right? Okay, so I actually think that active learning is actually more powerful than just like labeling. Like if you think about active learning differently, I will actually show you this. So this is the way we as data scientists used to think about the way we do our work. We would first build a data set, right? And so I actually even call that data science PTSD. 10 years ago, when it was hard to get data, you would just like focus on like, I need to gather data even if I don't know what I'm gonna do with it. And so basically you would not have the opportunity to get the right training set. Not necessarily the right features, not necessarily the right quantity, not necessarily the best practices that you need to put around creating a data set. And then later you would take this data and build a model for it. So basically you would be forced to adapt the model to the data and not the other way around. Because we have big data today and we can get picky about the data we use, and because collecting data is becoming easier and easier, you can actually simultaneously build a model and your data set, the data set that goes with it. And this is really what active learning actually offers you. All right, so let me show you exactly how this works. So active learning basically is it's basically a process where you incrementally add more and more data into your model as you train it. So you start with unlabeled training set, and then you will select some rows within this unlabeled training set that you will label, and then depending on your results, you will add more and more and more. And so this approach is called like pooling active learning. So let me show you a little, I'll show you that, and then I'll show you a quick demo of how this works. So basically active learning is about getting better learning curves. What you see, the graph you see over there is basically like showing like the y-axis shows the accuracy or the quality of the model, and the x-axis shows the amount of labeled data. And so what you see in gray is what you would have if you were to throw more data randomly. So like as an incremental supervised learning. So you're incrementally adding more and more data, but there is no intelligence in the way that you decide to add data, right? I mean, so each one of the samples that you add incrementally are going to be randomly selected. Of course, the accuracy goes up because we all know that the more data, the higher the accuracy is. Active learning is about like allowing the model to learn faster. So now if you have the option of deciding what data you want to put into the system and you know which one is going to be the most beneficial for your model, then you can have the model learn faster and reach higher accuracy even faster, right? And so in this case here, if you see the little dots over there, so you can reach 80% accuracy with that specific model using like 45% of the total size of the data set or the training set versus like 70% if you were not to use active learning. There are cases where it's much more than that. I've seen cases when you actually you only need like 10% of the data to reach the same accuracy. So this is basically the way it works for pooling. So this is like as clear as I think I'm gonna get here. You have a large pool of unlabeled data. It's available to you, you've collected it. And so then you have to select an initial sample. The problem with the initial sample is you don't know anything about the data because this data is not labeled and you've not done anything with it. So it's like an explore-exploit problem. You have to guesstimate at first which one of your data set, which one of the data points within your data set are going to be the most beneficial. And then you take this small sample and you send that to a human oracle. It can actually be a machine learning oracle that's going to provide you labels for this. Now you have a labeled initial sample, right? And you will basically use this data to train the model that you have. Of course, because you didn't use a lot of data, you don't expect to have a very high accuracy, but probably higher than if you had like randomly selected your training set at first. And so now you have a small labeled training set. You have a trained model, not with a really high accuracy, but it's available to you. So guess what? You're gonna use this model now, and you're going to use this model to infer the labels on the remaining of the data, right? And so, so basically, these are synthetic labels at this point. Now, the cool thing is, like, since you run an inference, you're going to have metadata on your on basically the entire data, right? I mean, so you'll have things like entropy, like confidence levels. You'll get like margin between like the first best prediction and the second best prediction, and so forth and so on. And so all of this metadata that you generated helps you identify what is the most useful. The most useful strategy to pick your next sample, and then once you've done that, you actually throw that so that this human annotator can give you real labels. It's a very powerful technique because you're not actually using synthetic labels at no point in time. Like other semi-supervised learning approaches are dangerous because you use synthetic labeled data, right? And so in this case, you just use synthetic labels to identify what data you should label, but at the end of the day, you're using real labels provided by humans or like a good machine learning model to basically tell you what these images were in this specific case. And then you start over. So you have more data, you add this data into your model. You're still going to use the data you had in the first place. And now you hope that your accuracy is going to go higher and higher and higher. And so eventually you stop when you decide that your accuracy is high enough, or you run out of budget if you had a specific budget for labeling, or if you run out of time, and so forth and so on. So there are different like reasons how you would stop. So how, like intuitively, how does this work? So this works because, like, in this specific case here, right? I mean, so I have lots of data points over there. If I run a linear regression model over this, I would get the line that you see on the picture. If I have like I had this extra few points over there, you can see like the type of difference you would have here, right? So if you were to randomly pick like and sample out of all these points, all the blue points, the dark points, and the light points, you would basically have well, I mean, if I randomly pick things, I would get more points in the blue part to the point that maybe I only get blue points, like light blue points, instead of getting, so basically I would get this dotted line instead of having the hard line over there. And so basically it tells you that you have to be intelligent in the way that you do your random sampling, and you have to understand from here that the dark blue points are actually more valuable because they are more restrictive, they're giving you more restriction on your model, and so it helps you learn faster. All right, and so basically what you have to remember here is like not all rows are equally, are created equal. All right. So now let's like go like really quickly in different strategies. So what you saw is like called pooling. You have another type of strategy called streaming. Streaming is basically you decide not to use or not to use a specific data point based on the threshold that you put over there. You can say like I'm gonna reuse whatever data that for which I did not have 80% accuracy. I had less than 80% accuracy. And decide to use that to retrain your model as you go. Problem with that, you cannot constrain your problem, right? Yeah, I mean, so basically, like if you're unlucky and all the data that you inferred was less than 80% accuracy, then you're gonna use all of your data and you're basically gonna have a supervised learning approach. Pooling is basically what we saw before, so it's really great for our business case because people are trying to minimize their budget, and so this helps you keep your budget under control. So how do you pick data smartly at every single active learning pool? There are lots of different ways to do this, and so one of them would be like something called uncertainty. Uncertainty would be based on confidence level, knowledge from confidence level, from margin sampling, from the entropy of the data, and so forth and so on. The other would be like query by committee. Query by committee is basically you use several models, like an ensemble method, and you try to see in which cases the models disagree. If they disagree, you would actually consider that this data point in particular is difficult to learn, and so therefore you would add that to your training set, label it, and move forward. And then you have much more sophisticated kind of strategies based on like expected model change. So this is even cooler because like you would basically pick a specific data point and try to predict if the level of information you would gain would actually be beneficial for your model. And so basically like at that point in time, you would be doing something that's more of the order of like Monte Carlo simulations and so forth and so on. So you basically try to identify which data points in your training set would be the most beneficial for your model. So why is this so complicated, right? I mean, so we've seen that you have like pooling and streaming. You also have something else called synthetic query generation, which I will not dig into. Picking the querying strategy is really hard. In fact, there is no framework for it. And this is one of the things that we started working on at Figure 8. Because people try and see if it works. Like usually the way you go by this is just identify like this seems a reasonable querying strategy. For instance, I'm going to take the 100 lowest confidence levels among the infer data to as a querying strategy in my active learning loops, but you cannot know in advance if it's going to work, and you're not going to know if it's the best one for you. Pooling size, how much more data you want to add at every single loop, and how many loops do you want to use before you stop. And so for all of this, there is no framework on the market, and there is literally no research on that topic. People, like whoever is doing active learning, even in academia, is doing they're doing research based on guesstimates. I believe this querying strategy is going to work. I will try it. If it doesn't work, if it works, it doesn't work. This is what I report in my paper. All right, so really quickly, so misconceptions are about like active learning in general, right? So I will say that active learning is not a type of model, it's actually a wrapper or strategy around the model. So it means that you can do deep active learning. You can leverage active learning regardless of the type of model you're using. So you don't have to change your model, you can actually go ahead, use the model you have and go and improve on it. Other misconception would be like it's a mathematical formula. It does not need to be a mathematical formula. The querying strategy is actually a sampling strategy that you use to like identify what the best next pool of data is going to be for you, and it can actually be something that's non-deterministic. It can be a specific way to sample that's not random sampling, right? All right, so why do you want to, like, I will give you an example of something that happens on the market. Typically, people use, like, they look at the confidence level of the data they've inferred, and they would use the data with the lowest confidence level. And this is a bad strategy because you might actually be throwing spam into your system. What we've actually done at Figure 8 is we basically take medium confidence, we take among this medium confidence sample, some of them being the lowest within that sample, the highest confidence within that sample, and then some randomly sample in the middle to ensure you don't induce any biases. This would induce biases big time because you're actually throwing data that seems to, like, is potentially going to be spammy. And then the other problem we've seen is, like, people believe that at the end of the day, if you want to reach the very maximum accuracy, you still need to use supervised learning because the more data, the better. However, if you use active learning because you're actually in the business of identifying what data is helpful or not helpful, you're doing a better job with overfitting because you're ensuring diversity of your training set. You may also be able to remove spam automatically. And so in some cases, you actually get a higher accuracy even if you go all the way using active learning because you inject your data in a different order. My conclusion. All right. So what do we want you to remember here? So good data is important for machine learning, specifically if it's labeled. We do have a problem with big data labeling crisis these days. So as we've seen, you can label faster or smarter. So my suggestion is let's try to label smarter. About active learning specifically, so as you've seen, like, it allows you to improve on your accuracy. It is an enhancement on your existing model, so you don't have to give up whatever model you're working on. You just need to add this piece of intelligence on top of it because it's a strategy and not a model. And unfortunately, it can be difficult because there is no framework currently to identify the right querying strategy, but there is more research coming on that topic. Thank you.